Hello everyone. Today we will understand modeling t-square statistic and um, as you know that we have dealing with right now multivariate task, and modeling t-square statistic is a multivariate generalization of the student t-test. So where we perform student t-test in a single one, and now with a multivariate task we will use modeling t-square just like that. It's used to test the hypothesis about mean vector of a multivariate normal distribution when the variance covariance matrix is unknown. Okay, this is a little description. You can read it yourself. The main task that I'm going to follow as a definition, the mathematical definition, the Hotelling t-square statistic is given by like this one. And in more formal way, if you wanted to write like this, you can say that consider x1 x2 up to xn the sample observation of size n of a p-dimensional multivariate normal distribution like this, mu and the variance covariance matrix. So you can write like that, and then you can define that. Then the Hotelling t-square statistics will define like this one. And in short, you can identify what exactly what is. N is the sample size, x bar is the sample mean vector, mu is the hypothesized mean vector. You can write it like mu naught or as well also. S is the sample covariance matrix, yeah, like this one. So this is actually what is Hotelling t-square statistics. We will see how we can derive this one. Okay. The next task is about the properties, very important properties, and it is very important for the exam question as well, because I have an exam question here. The first one is, what is Hotelling t-square statistic? What are its properties? There is a 3 marks question can be asked from you. Okay, so there are the properties. When the null hypothesis is true, the Hotelling t-square statistics follows F distribution. So mainly task is Hotelling t-square follows F distribution by the condition like this one, and there is a specific proof for this kind of properties, but I'm not showing you here. Invariance properties, very important properties, that the statistic is invariant under non-singular linear transformation, meaning that if the data is undergo a linear transformation, when the data will perform inside a linear transformation, t statistics remain unchanged. There will be no change in the t statistics. That's why it's called invariance, not changed. Generalization of t-test, as you also know that this is one the generalization of the p-variate of multinormal task and asymptotic behaviors, and as a sample size increase, the distribution t-square approaches chi-square distribution, and that is actually the asymptotic behavior of Hotelling t-square statistics. Independence, Hotelling t-square is independent of the change of origin and scale. So these are the two things, origin and scale, and these two things Hotelling t-square is Hotelling t-square is independent from origin and scale. Univariate t statistics, the univariate t statistics for testing the hypothesis that population mean mu equal to hypothesized value mu naught, then the given task will be this one, and how you can change it to this part. And multinomial multivariate Hotelling t-square statistics, this is the already given. Okay, now this is not the case. The main case we are dealing with, uh, okay, so forgot that this is not the properties was up to this point, and now we are talking about a special case. uh, okay, now we will answer this question. Show that Hotelling t-square is generalization of univariate t square n minus 1. Okay, very much enough. So we begin with this answer. The Hotelling t-square statistic for p-dimensional mean vector of mu given by this one, as you already know that, but we wanted to prove this, how it's come from. We wanted to prove this one, how it is coming from, where part. So you have to basically understand some few things, and these things will be lead you to here. So in univariate case, what we have, we have in univariate case t is equal to x bar minus mu naught divided by s root n. That was the formula because we wanted to test as a null hypothesis. What we wanted to test, mu is equal to mu naught. Okay, we wanted to prove this, mu is equal to mu naught or not. So from this one we can square both sides, right? X bar minus mu naught whole square s square divided by n. And then what we can write, we can write yeah, what we can write, no, basically we need t square here, and this n will be multiplying like this one, x bar minus mu naught whole square, and this s square will be s to power 2 like this one, or you can s squared to inverse 1, you can give it like, and you express that in two parts. Then you can write as x bar minus mu naught s square inverse 1 x bar minus mu naught, this one. And whenever you will perform for p-variate task, then it will become like this one, t square is equal to n x bar minus mu naught is exactly s squared, right? S squared, so it's squared, or basically there is a mistake that I have to deal with. Now what we can write, this one as a, when it's prevariate, we consider this one as a, this one like this, is inverse of x minus mu naught like this one, and this one will be in the transpose one. So this is actually the p-variate for p-variate multinormal task. So this is the multivariate task. Okay, that then this will be generated, and this is the how you can generate this one, right? And now what you can write as a, so this is the approach when you go from univariate from p1 up to p-variate. You can say that this is the multivariate one. Okay, and here in this part we tends to go from the substituting this into Hotelling t-square formula. So since the transpose of a scalar itself, then you just transforming it, the expression is equivalent to the squared univariate t statistic, and this expression is nothing but t square like this one if you match this one. So we are going from p-variate to univariate task. Basically here what is happening, distribution relationship, the distribution of t square when p is equal to 1 follows this one, t square is equal to small t square, which is follows if distribution 1 n minus 1. Then we can write this one as well. Therefore the Hotelling t-square statistic is a generalization of univariate t square n minus 1 statistics, as it reduces to familiar univariate from when the dimensionality is p is equal to 1. Okay, this is the task. That is how you are going to prove this one. So thank you very much.